In this lesson I'll be talking about calorimetry, but before I go into any specific details about calorimetry, I would like to explain the concept of specific heat capacity. If you look at the diagram above, we have 1 gram of water represented by this solid cube, and if I was to increase the temperature of 1 gram of water by 1 degrees, the energy required would be 4.18 joules. Similarly, if I have a gram of water, but this time I've increased it to 2 degrees, the energy required to heat 1 gram of water by 2 degrees centigrade would be 2 times 4.18 joules, which would be 8.36 joules. Applying exactly the same concept, if I have 5 grams of water and I want to increase the temperature by 1 degree centigrade, I'd multiply by 4.18 to give me 20.9 joules of energy. So this amount here represents how much energy I require to heat this amount of water by this temperature. A slightly more complex example of this would be 3 grams of water being heated by 10 degrees this time. Now remember, this figure here, which is also known as the specific heat capacity of water, is the energy required to heat 1 gram of water by 1 degrees. I want to heat it to 10 degrees more than what it was, so I multiply by 10. The mass of the water in this case is 3, so I multiply by another 3 to give me 125.4 joules of energy. Now, different substances have different specific heat capacities. If we look in this example, copper being heated by 1 degree centigrade requires 0.39 joules of energy. Remember, in the case of water, for H2O, this was not 0.39 but 4.18 joules of energy. So we can clearly see here that there's a significant difference between heating water by 1 degree and heating copper by 1 degree. So the specific heat capacity of copper is 0.39 joules, for water is 4.18 joules. If I had 10 grams of copper and I want to heat these 10 grams by 5 degrees, the energy required would be 10, which is a mass of copper, 5 because I want to heat it to 5 degrees more than what it was, and the specific heat capacity for copper, 0.39, gives me a total of 19.5 joules. Combining all the information from the previous slides, we can actually derive an equation which basically means the energy required, which I'm going to call Q, is equivalent to the mass of the object being heated multiplied by the energy needed to make 1 gram of the substance 1 degree hotter, which I have called specific heat capacity, multiplied by how much do I want to increase the temperature of that substance by. Gives me the equation Q, or the energy required, is equal to the mass of the object being heated multiplied by the specific heat capacity multiplied by the temperature rise of the substance. So here we have the full equation now, which is Q, the energy required, is equal to the mass of the object being heated multiplied by the specific heat capacity of the object multiplied by the difference between the initial temperature and the final temperature. A reminder here that the specific heat capacity is unique to each particular substance. And if you look at the previous examples, it was 0.39 for the copper and 4.18 for the water. Up to now, we've looked at a substance being heated up by heating up a certain amount of a mass, multiplying by the specific heat capacity and looking at the temperature difference. The thing that we haven't looked at is what is actually providing this temperature rise. An example I can give you is, if we look over here, imagine I have a beaker. I'm taking 50 grams of water in that beaker. I have inserted a thermometer into the water and I note down the original temperature. For argument's sake, I will say that the initial temperature, or initial T, is equal to 20 degrees centigrade. Imagine now I begin to heat up the water in the beaker with a spirit burner shown over here. So I heat up the mixture using my spirit burner from here, and now the final temperature is equal to, again for argument's sake, 40 degrees centigrade. The difference in the temperature, or delta T, is the difference between this temperature, 20 degrees, and this temperature here, 40 degrees. So delta T is simply the final temperature minus the initial temperature. So that equals to 40, take away 20 is equal to 20 degrees centigrade. The specific heat capacity again for water is 4.18 joules, and my mass is given to me over here. So Q is equal to mc delta T. The mass again was 50. C is always 4.18 for water, and delta T in this case is 20. If I multiply out the complete equation, I end up with the figure 4180 joules. Again, up to here, I know I have this amount of energy given out, but what I do not know is how much energy I've put in. And in order for us to find out how much energy is given out per amount of fuel being used, we look at this equation over here. We can take this value from the previous slide, which is 4180, and divide it by the moles of the reaction. In other words, how much ethanol moles have been utilized in warming the solution up by 20 degrees centigrade. Looking at a complete experiment now, imagine I had propane, C3H8, and I had 0.6 grams of the propane. I have completely burnt this in oxygen, and the heat given out by this process increased the temperature of 100 grams of water by 64.9 centigrades. And we're going to use this data now to calculate the enthalpy of combustion of propane. So again, going back to our Q is equal to mc delta T, the mass of the water given to us in the question is 100 degrees, which is equivalent to my M. The specific heat capacity of water will always be 4.18, and this figure will be given to you in the exam. And my change in temperature, the difference between the initial and final temperature, is 64.9. Put all these values into the equation. Q is equal to 100, which is a mass, 4.18, which is specific heat capacity, 64.9, which is a change in temperature, to give me a difference in energy of 27,130. This is my Q value. Delta H now is taken into account how much moles of fuel I have used, and this is where this 0.60 grams quantity is going to come into use. So first of all, I work out the moles of propane. How do I work out the moles of propane? The normal way, I divide the grams of the propane by the relative molecular mass of propane, and this gives me a figure of 0.01364. I then take again this equation over here and substitute the values in. So where did this figure here come from? 27.13 is the equivalent of this figure over here in kilojoules. So I've just divided that by 1000, and the reason why I have a minus figure here is because it's an exothermic reaction, and every time I have an exothermic reaction, heat is given out. Therefore, we include a minus sign. Divide the value here, Q, by the number of moles, which we just worked out over here, and we figure out that the enthalpy change of the reaction is minus 1990 kilojoules per mole.